Hey class, Adam Ward here. I want to talk with you in this lecture about anaerobic digestion of sludge. We're going to talk just a bit about how and why that process works from a microbial standpoint, and we'll end with sort of the key design criteria and typical operation. Okay, so this is sort of our typical unit process layout. And in red arrows here, I'm trying to show you the flow of sludge that we're dealing with. Both anything that we settle out of the primary clarifier, and so of course that will be organics that came in. Those haven't necessarily been digested yet, as well as anything that comes out of the secondary clarifier. And so those are the microbes that we've basically grown in our aeration chamber and settled out. So the reason that we go through anaerobic digestion of our sludge is to stabilize the sludge. And that has three primary purposes. So one is we want to generate a product or generate a material that's not going to continue to degrade and change dramatically. So we don't want a lot of reactions happening in this material. So we want it stable. That stabilization is going to have the consequence of reducing odor. Because that odors typically would be produced by some sort of a microbially mediated reaction. And this process is also going to reduce the pathogen content so that we're not taking fecal bacteria and putting them basically back onto the landscape or having to deal with them in what we dispose of. So all of this together, the combination of those three processes gets our sludge into a place where we can dispose of it adequately. So what are we actually up to here? We won't get into much specifics of the biogeochemistry that's taking place here. For our purposes, it's enough to know that we're going to take organic matter and some small amount of oxygen that's combined with other constituents as we go into this digester. We're keeping it anaerobic, so we're not supplying oxygen, we're starving it. And the anaerobes, the bacteria who will thrive in those conditions, will use the oxygen out of those combined molecules to produce new cells for cellular respiration, and will generate a host of other products, notably including methane gas, carbon dioxide, and several other minor products. And so to give you some examples here, organic matter, you can think of things like carbohydrates, proteins, fats, and oils that would end up in the sludge. Combined oxygen, there shouldn't be much oxygen in the O2 dissolved oxygen form, but there will be several molecules that have oxygen as part of them. And the class of microbes that we call anaerobes are able to strip those oxygens out of the forms that are written down here as examples. We've got the whole microbial ecosystem, both their growth and reproduction and their respiration being supported. Methane gas, CH4, which presents an opportunity for us to recover natural gas from the system and actually gain some energy back. And other more minor products, a few examples of which I've listed here. So in general, this is the set of reactions that we're trying to get to take place. There's really four steps that happen along the way. So first we start with complex organics, so things like carbohydrates, lipids, and proteins. And those are going to get transformed into simpler soluble organics like glucose, amino acids, and fatty acids. And the process by which this happens is called hydrolysis. And for your purposes, what you need to know is hydrolysis is the process by which those complex organics are being broken down into simpler constituents. Those soluble organics are then in turn converted into organic acids. Ultimately, we're after acetic acid in this process, but there will be other more complicated organic acids that form, things like lactic acids. Well, there's sort of a two-step process between soluble organics and the organic acid. The first one is acidogenesis, and this is basically the process of fermentation. So we're taking those organics and we're converting them into volatile fatty acids. And then those fatty acids are used as an input in the process of acetogenesis, and they're turned into acetic acid. and that's CH3COOH. So both of those steps are sort of happening in tandem to form a host of organic acids in the digester. And that third and final step is the methanogenesis. So this is taking the acetic acid as an input, and there are microbes, methanogens, who will convert that into methane plus CO2, and we'll get some other byproducts from that as well. So these are the four key forms that our material will be in, and the key transformations that occur in between those groupings. Now, overall, when we set this process up, anywhere from 40 to 65% of the volatile suspended solids that we send into the digester will actually be destroyed. So they will be converted into, ultimately, methane and CO2, and the remainder will pass through. So just to kind of get our heads around how one of these digesters works, these are very carefully controlled reactors. And so they will typically be run at a fairly warm temperature, anywhere from 29 to 35 degrees Celsius, warmer to accelerate the breakdown process. We'll typically run at approximately a neutral pH, and we'll see in a few slides why that is. And you can see that we may be having to control alkalinity as well. 1,000 to 5,000 milligrams per liter as calcium carbonate. So think back to our water softening calculations there, where we can use lime or quicklime to control alkalinity if we need to. And we'll typically run this with volatile acids anywhere from 50 to 250 milligrams per liter of acetic acid. And again, that we don't want it getting too acidic, and we'll talk about that in just a moment. So those typical operating conditions, what we're going to generate is largely gases that come off of this. Methane representing anywhere from 55 to 75% of the gas, and carbon dioxide anywhere from 25 to 45, the balance being a remainder of much more minor gases, hydrogen gas, nitrogen gas, for example. We expect that anywhere from 50 to 75% of our volatile suspended solids are going to get removed by this process, and that should equate to up to half, 35 to 50% of our total suspended solids. Of course, some of those solids weren't volatile to begin with, and so those are going to pass through the sludge treatment process. In gas production, we might expect to be anywhere from about 0.75 to 1.1 cubic meters of gas per kilogram of volatile suspended solids that we destroy. What can go wrong in this process? Methanogens in general are pretty sensitive, and so getting the optimal physical and chemical conditions to let those methanogens thrive is a tricky balance that has to be maintained. So there's a few processes that we need to think about. The first being the process of acidification. And so, excuse me, our methanogens are really only happy at circumneutral pH. In fact, as soon as we drop pH below about 6.5, those methanogens tend to get inhibited by the acidification. So there will be other bacteria that can thrive, and those methanogens themselves will start to see toxic effects happening if they're in that acidic of an environment. So we're really focusing on keeping the pH at a particular level. This is somewhat tricky because the step that precedes methanogenesis is the production of acids, right? Both that fermentation step and then the creation of acetic acid. And the bacteria who are responsible for those will be inhibited if we get below 5. Now, taken together, what happens in between, so if your pH is less than 6.5 but greater than 5, you're getting that first step. You're generating the acids, but then the methanogens aren't able to process those acids. And so this is what's called pickling of your sludge, is basically that you create an environment where those methanogens aren't able to live. If they're not able to thrive, you don't finish that removal process and generate the methane and the CO2, And so not only have you pickled the tank, but your sludge is not getting the treatment that you want. You're not removing any of that mass. So as a consequence, one of the things that's important in this step is carefully monitoring the pH and occasionally keeping check on the acetogens, so the microbes that are generating acid versus the methanogens. So you want to keep a balance so that those acetogens don't overwhelm the process and get the pH dropping precipitously. So that's acidification. Toxicity is another issue that we have. And so on this slide, I'll give you just a handful of examples of various substances in the left-hand column when they start to inhibit the process that we're after at concentrations in milligrams per liter in the middle, and when that's a very strong inhibition on the right-hand column. And so as an example in blue here, we can get a sodium toxicity if we get over in that range of 3,500 to 5,000 milligrams per liter, with strong inhibition if we get up to 8,000. And I'm going to go ahead and write on similar values here for potassium, for calcium, for magnesium. It's not important to me in this class that you learn what those levels are. I simply want to point out that these methanogens can be quite sensitive. And it's not just to cations. I just started with cations in this case. But there's a whole host of other compounds that can be toxic to our methanogens. So ammonium, sulfate, copper, chromium, nickel, zinc. And so maintaining a healthy ecosystem for those methanogens is a really critical part of this process. Those methanogens are extremely sensitive to changes in temperature, to changes in pH, to acute toxicity or inhibition associated with any of these high concentrations. All right, so we've got a sense of what should be happening. We know some of the major problems. How do we design one of these anaerobic digesters? And we're going to think here of a simple anaerobic digester, so one that does not have any recycling as we did in our activated sludge basins, for example. So just a simple anaerobic digester. One of the things that we've got to watch out for here is washout, and so we need to make sure that we give these methanogens plenty of time to grow and actually do the processes that we want them to do. And so just like we did before, we'll calculate a minimum solids retention time. And we can do that with the equation here. And I'll note that I did not have the subscript min on it, but what I'm circling in orange there, that theta C, that should be theta C min. So the minimum retention time to achieve washout is the case when growth and death are balanced, as we see on the right-hand side. Just to give you a reminder of what these things are, Y, capital Y is yield, and again that relates the mass of BOD in the denominator per mass of volatile suspended solids that you can generate in the numerator. And a typical value there might be 0.4 grams per gram. That lowercase k in the numerator up top, that is the maximum rate that the substrate could be consumed, and that is in mass of BOD per mass of volatile suspended solids per time. That's that capital T on the bottom. And we know temperature is extremely sensitive, and you can see there's an Arrhenius equation formulation here that'll let us calculate this using the correct temperature in degrees Celsius that we plan to operate at. And that'll have units again of grams of BOD per grams of volatile suspended solids per day. Continue working through the equation. That capital Ks is the half saturation constant. And again, that's describing to us how rapidly this reaction can occur. You'll see that's also got an Arrhenius formulation given here. Grams of BOD per, that says length cubed, so that should be meters cubed, for example. S in, concentration of biodegradable substrate in mass per cubic meter. And finally, out on the end, that decay rate, K subscript D, and yet again we put the Arrhenius equation formulation there. Hopefully, one thing that you're seeing in this slide is all of these have been formulated with the Arrhenius equation, so you can correct for temperature. That's critically important because these methanogens are extremely sensitive to temperature, and this can have a major impact on our design. So we'll always want to watch out for temperature in a design problem here. Okay, now with theta C min, just to give you a sense of what a typical value might look like, minimum solid retention times may be as short as 4 days if you're keeping that at a warm temperature, so 35 to 40 degrees C. If you drop that approximately in half, you're up to about an 11-day minimum retention time. And for design purposes, we'll often use 2.5 times that minimum. So your design process up to this point would be calculating that theta C min, and you're doing so by temperature correcting all of the various rates and coefficients. And whatever you get for that minimum time, you're going to multiply that by 2.5 to get the design time for your reactor. A couple other notes just to sort of give you a sense of how these things might be sized. What's a typical loading rate? Anywhere from 1.9 to 2.5 kilograms of volatile suspended solids per cubic meter per day. So that would be a typical rate to help you get a size of reactor. And certainly if that value gets above 3.2, that's where we would start to get worried about washout of our methanogens. So this gives you at least a typical range to work from and an upper bound that you can check that you are staying within. How much of those volatile suspended solids are we able to actually process or destroy? One approximation is given here. So you'll notice it's got that design time on the right hand side, theta in days, and the equation written here, 13.7 times the natural log of theta plus 18.9. That should get you the percent of volatile suspended solids that you'll actually destroy or process. And again, we saw this earlier, but just a reminder, every kilogram of volatile suspended solids that we destroy, we're anticipating anywhere from about 0.8 to 1.1 cubic meters of gas getting produced. That's total amount of gas, and we saw early in this lecture how you could convert that to estimate methane or CO2 production. All right, folks, that's what I have for you. I hope this helps you get a sense of what are the biogeochemical transformations that are taking place inside of that reactor, some of the nuances of how and why this thing functions, and a little bit of guidance to help you in design. I will see you all in the classroom. Thank you.